But before the class, any question regarding the milestone one assignment? I know everyone has submitted. Some of you have done the reflection. Some of you haven't, but it's okay. Okay, it's just a reflection. Okay, try again. Next milestone, I think. So now let's move on to the second milestone. Please read about milestone 2. If you don't understand, ask. Okay, and don't do it last minute. Sorry, don't do it at the very last minute. Do it early. Prepare early for the milestone 2, because the submission time for the milestone 2 is close to your test 1. Okay, so don't do it at the last minute. Right? Okay, so in the last class, we have talked about how to represent negative number. And in this class, in this lesson, we're going to talk about the fixed point numbers and also the floating point numbers. So in these subtopics, when we talk about the negative number, I mean, we are using the 2's complement representation. Okay? Right. I can use this. Okay. Real numbers are numbers that contains fractions, and I did mention that integer is also a real numbers, because integer is also a fraction, okay, of 1. Okay. Fraction something over 1, so that is an integer. All right. But these fractions are not supported on the integer hardware. So your hardware cannot represent integer. Okay. Your hardware do know what your hardware only knows 0101, but they don't know if that is a real number, integer, fractions, irrational number, and so on. Okay, so we need a different representation. Okay, and there are 3 types of representation for a fraction, which is a fixed point. Okay, that is written like this. Okay, and it is sufficient for a simple application. Okay, remember, fixed point, simple application. And then there's also rational number, but it is not commonly used, and we're not going to look into this also, so you don't have to worry about this. And another one that we're going to talk about is a floating number. Okay, I'm not sure if my WhatsApp notification is bugging you. So I'm just going to close WhatsApp now. All right. Okay, so there are 2 representations that we are going to look into. The first one is the fixed point, and another one is floating point. Okay. Now we're going to look at the Q format, or which is for the fixed point. Fixed point representation. Okay. The Q is a number format for fixed point numbers. Okay, and it is written as QM dot N or QN. Okay, where the M is the number of integers bit, which is optional, and N here is the number of fractional bits. So the integer is optional because our main focus is to represent fractions. So you can write, okay, the number as QMN, such as if it is an 8-bit, you can have QN 7, 0, where the integer is 7 and fraction is 0, no fraction at all. Or you can write, you can have Q07, okay, where the fraction is 7-bit and there's no integer at all. But this is also equal to Q7. Okay? Since the M is optional, the integer is optional, we can skip the M and just write Q7. Okay? Or sometimes we write it as Q.7. Same thing. All right? So the total number of bits in the data word is the sign bit plus M plus N. So when we talk about 8-bit, 8-bit, so the first 7-bit, so bit 0 to bit 6 is for the magnitude number, okay, and the MSB or the leftmost bit is for the sign bit, okay, 0 or 1. So here we have in the example here, okay, example of 8-bit Q format numbers, we have Q70, okay, Q70, where 1 bit at the leftmost will be the sign bit, and then we have 7-bit of integer. And then we could have Q61 for an 8-bit Q format numbers. Q61, we're going to have 1 sign bit, and then 6 integer, and another one is 1 fraction. Okay, let's, in case you don't know what is integer and fraction, let's look at some decimal example. So if it is 1234.5678, so this part is the integer part, and this part is the fraction part. Okay. But in binary, we're going to need another bit here at the leftmost for the sign bit. Okay, so here the blue part is the integer part, okay, and the red part is for fraction. Okay, your binary point, so this is a decimal example, so this is a decimal point, right? Your radix point. This decimal point in the binary is just an imaginary point. Not related to imaginary number. It's just imaginary point means we don't put it, when we save the number, we don't put it, we don't put the binary point, but we know, okay, this is a, as a designer, we know that this is a fixed point format, Q format. All right, moving on. If the format is Q34, so you have 3 integer and then 4 fraction. Q07, or you can write as Q7, this is with the maximum 7-bit fraction. Okay, so the decimal range for this is the binary number add to the fraction number. Okay, the binary part add with the fraction part. So for the Q70, since there's no fraction, the decimal range is equal to the 2's complement, okay, because we have 1 sign bit and then 7 integer bit, okay, and this follows the 2's complement, so the decimal range is between minus or negative 128 to positive 127. Okay. And for the Q61, okay, the range is smaller here, but we can have more precise range. More precise range with 0.5 value, okay, because we have 1-bit fraction here. Okay. So the bigger the fraction number is, you can have more precise number representation. Okay. If your system needs accuracy, so you need to use a fraction, okay, or a fixed point, or a floating point. Right? Moving on. Okay. The Q format stored and manipulated as regular binary sign integers by standard integer hardware. This means, okay, in the hardware, the Q format is stored like this. Okay. Your hardware doesn't know that this number contains binary point. Okay. Or in the hardware, we can only see that the number is just as regular binary, or sometimes we call as natural binary. If there's no sign, so if it is signed, we say regular binary signed integers. Okay. If it is an unsigned binary, we also call it as natural binary. Okay. Your hardware doesn't know that your numbers, integers, has sign. Okay. Okay. So you as a designer has to interpret the number yourself. Only you know how to use the number. Okay. Only you know how to wire the hardware to make it how do I say? To make it a fraction number. Okay. To make it significant as a fraction number. Right? And there are two conflicting notations where sometimes some some scholars count the sign bit as integer, and another scholars doesn't count the sign bit as integer. So we're going to use the first one here. Okay. So when we say 8-bit integer, we're not count the sign bit. So we just going to write as Q70 instead of Q80. So you don't have to care about the number 2 here, because we're just going to use this format in this course, right? But don't be shocked if you found references on the internet where it says 8-bit integer is denoted as Q80. Okay? Some scholars have different point of view, right? But to avoid confusion, the total number of bits must be specified. So what is the total number of bits? Okay, here, total number of bits in the data is sign bit plus m plus n. So total number of bits is sign plus the integer plus the fraction. Okay, and then choosing the position of the binary point depends on the largest number needed for the given algorithm and the tolerable error when we require a precision. So the largest number needed for the given algorithm means how many bits needed in integer part. Okay, so that you can look better. The longer number of bits in the integer, okay, the decimal range will be bigger. Okay, you can have bigger decimal range if you have longer in bits in the integer part, okay, in the m part. But you need to also consider the tolerable error. Okay? How many percent error of the calculation, okay, that is acceptable in your system. So this one, when we require precision, okay, we need fraction. Means, okay, the longer number of bits in the fraction, you can have a longer fraction. Yeah, means more precise. Okay. Longer fraction means more precise. Am I right? Longer fraction, more precise. Okay. For example, in decimal. Okay. So if you have 2.3, 2.3 in decimal, so this is more precise than 2.0 or 2, right? Just 2 without the fraction, because 3 is round up to 2. But we can have more precise value if we have longer fraction part, right? 2.31, for example. It is more precise. 2.31235. So the longer the fraction part, okay, more precise your value is. All right. So now let's look at the Q format in the binary. Okay. So the MSB is the sign bit. Okay. Sign bit. And then we have the integer part, and we have the fraction part. Okay. But when we want to find the decimal value, of the Q format, okay, we need to calculate the sign bit here, but we put the negative, just like we translate the 2's complement. Just like when we translate the 2's complement, okay, the MSB or 2's complement is count, but with negative. Then the sum of the weight of the rest of the bits is count as a positive, right? But for fractions in these fixed numbers, okay, so the integer part, it has its calculation. I think you have learned this in digital electronics. So this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, right, and 2 to the power of 3. But on the fraction part, is 2 to the power of minus 1, is 2 to the power of minus 2, 2 to the power of minus 3, and 2 to the power of minus 4 here. Okay, and this is actually 1 over 2, 1 over 2 to the power of 2, which is 1 over 4, is 1 over 8, 1 over 16. Then you get 1 over 2 is 0.5. And this is 0.25, 1 over 4, and so on. Right? Okay, I hope you still remember how to interpret the fraction or translate the binary. Okay, convert the binary in fraction to decimal in fraction. Let's look at the example here. So if we have a Q34, where there are 3-bit integer and 4-bit fractions. Okay. So the weight is like this, and note that, okay, for the MSB, negative, because that is a sign bit. The rest is positive. So here, for bit value 0101, 1100, but it's a cube 34, means we have 3 integers and 4 fractions. Okay. So the imaginary bit will be here. Okay. Sorry, the imaginary point will be here between 3 and 4. Okay. So you can count this as this has been simplified. So the first one is negative. Okay. Negative bit over weight is negative 0 to the power of 3 plus 1 plus 0 plus 1 plus 1 plus 1 over 4. Okay. And add up everything and you got 5.75 in decimal. Okay. Or you can count it like this, where this is a general expression for an n-bit fixed point with the 2's complement number is given by, it's not in the slide, but it's in the textbook, page 68. Okay. Let me just write it here. Here. X is minus b and minus 1, 2 and minus 1 plus b and minus 2, 2. And so on, like this, until you find b0 to the power of 0. Okay. Like, you just have to worry about the position. This one, okay, don't think about point, okay, the binary point, okay. Just calculate this as usual as the normal binary. Okay. Calculate this as a normal binary, this part. And then you divide by 2 to the power of f, where f is the number of fraction bit, which is in this case Q34. So f here is 4. Okay. Right? To the power of 4. 4 is the number of fraction bit. Yeah. If this is not a Q format, if this is just a normal binary, okay, if this 0101110 is a normal binary, if you want to translate it to decimal, you just have to count this part, right? This part. If it's a normal binary, okay, if it's a normal binary, you just have to calculate this part that I highlighted in yellow. But if this is a fixed point in the Q format, okay, you divide that, okay, by 2 to the power of number of fraction. So the number of fraction here, you can find it here in the Q format names, right? Okay, questions? Right? Seems like no questions. Okay. Okay, now let's look at Q 0.7 or Q7 or Q.7. Okay. This is a Q format where we have 0-bit integer, no integer bit at all, and 7-bit fraction. Okay. 7-bit fraction. So, but it is an 8-bit binary because we need 1 bit for the sign bit. Right? So, the maximum value that we can get from the Q7 format is this number 0.99 to 1875 in decimal. Okay, but the minimum value, this is positive, and then the minimum value is minus one. We just can calculate the maximum and minimum value of a Q format, okay, by trying to find the decimal for the maximum value. It must be positive. Positive is bigger than negative, right? Then when all bits are 1, is maximum. All bits are 1. Okay. When the sign is negative and all bits are zeros, okay, that is the minimum value. All right. Okay, so later you will find questions like this. What is minimum and maximum number of Q3.4? So what is the minimum number and maximum number of Q3.4? So you have to calculate. You have to calculate when all bits, what is the biggest integer and then the biggest fraction that could be calculated when the number is positive. Okay, sign bit is 0. And then what is the smallest integer and fraction, okay, when the number is negative. So that will be the minimum. Okay, so in your test and final, we are not only discussing or giving question about 8-bit numbers. Okay, we can go up to 16-bit numbers because Q15 is more useful and human can count it like with just 16-bit. So yeah, there's a lot to do probably. And yeah, so you have to be able to count or calculate until 16-bit integer. Sorry, 16-bit binary. All right, any questions? Okay. No one is asking, then all right. Asir Sharif here. Asir Sharif is here. Please answer in the chat or using mic. Okay, looking for Asir Sharif Ahmad. Right. Okay. Bala Murugan. I'm just looking at your WebEx name. Sorry if that's not your name. Bala Murugan. My mic is on, right? All right. Bala Murugan. Anyone? Please answer me.
Yes, you can hear you.
All right, great. Okay, but I choose the correct person, right? All right. Let's choose someone else. Okay. If you change your name to Lenovo, then you'll be absent for this class, eh? Lenovo-san. Okay, change your name. Momen Mahgub Ahmad. Momen Mahgub Ahmad.
Yes, doctor.
Okay, Momen Mahgub Ahmad. So here we have found the minimum and maximum number of Q7. Okay, Q7. So can you tell me what is the minimum and maximum number for Q15? Q15. What is the minimum and maximum number for Q15? Can you use calculator to calculate? Q15 means we have no integer but 15 fraction bits. Okay. Okay. Lenovo is still check. Thank you. Okay. Q15. 9.
Okay, just give me a time to calculate it.
All right. Okay. Everyone. Okay. Minimum and maximum. All right. Meanwhile, just need you to know that this Q15 format, Q15 format is used to represent the electrical voltage in DSP application, means digital signal processing application. So that's why we use Q15 more than Q8, Q7, okay, 88 bits. That's why you will see later in your test and in your final, the question will be more on Q15 rather than the Q7. But it will take like a long time, so you might need to practice more. Okay, to practice more. All right. Everyone here in my class, you have you bought the textbook?
Yes.
Yes. Yes. Okay. It's a very
Yeah.
right. Okay. It's a very good thing to buy the textbook because as you can see the the slides here is not suitable for you to study. You cannot study the slides. You can only study the textbook or other reference. Okay. Well, if you don't want to buy the textbook, okay, you can also buy another reference book from Floyd. It's called the Digital Fundamental, and you can use that for digital electronics, digital system subjects, okay, and also another digital design subject, and probably electrical devices, electrical circuit and devices. Okay, it's a Pearson International Edition book. I will share with you later. Okay. It's just that the Pearson book is a reference book, and it is not compiled as in this course syllabus. You still need to find the chapters and everything. All right, we have an answer. Okay.
So doctor, for the maximum, I guess it's 7.125.
Why is it 7? Okay, it's
And for
Q15. Okay.
I think my calculator is it's
How do you
wrong.
calculate the maximum? How do you calculate the maximum?
I just used this formula to present it, to calculate it.
This formula?
Yeah, like it's like 2 to the 2 2 to
To the
the
power of 1?
2 to the power of minus 3
Right.
plus 2
Minus
to the
3?
power of 2.
2 to the power of minus 3 plus 2 to the power of minus 2?
2 to the power of 2, yeah, positive 2.
That is for maximum?
Yeah.
Why? Why? Give me a
What?
reason. Why? Why? Why do you think that should be the calculation?
Because I just followed the formula that I give.
Yeah? Okay.
Maybe I use it
So what's the
wrongly, I don't
formula?
know. Maybe I use it wrongly, but this is what I get from this lesson.
The maximum number, okay, the maximum number for Q15 is when you have 0 as the sign bit and the rest is 1. So it's Q15 means you have 15 fractions. Here is 7. 7 fraction. Okay. 15 bit of 1. See? All bits are 1. So why you only calculate minus 2 and minus 3? You should have calculated all the bits.
Oh, okay, I see.
Okay.
Can you show me the correct one? Because until now I'm not understanding well.
Okay. So Q7 is 0. Okay, the maximum for Q7 is 0. And then you have 7 bit of 1. Got it?
Okay.
Okay. Why? Because 0 is, which sign is it? Positive or negative? Moment. 0 is the
Yes,
sign for
positive.
0. Positive. Okay. So
Yeah.
positive number is bigger than negative numbers. So the maximum value must be a positive number. So we have positive sign here, and then if we have bit 1, we will count the value. If we have bit 0, we will not count the value. So to get the maximum number, all bits must be 1. So we have 7 bits of 1 here for Q7. But for Q15, okay, to find the maximum number,
We
the
got
sign must be 0. Right? Sign must be 0 because it must be positive. And then we have 15. Okay, we have 15. 1 standing. So when we want to find this in, if we want to find this in decimal, we have to use this formula. Okay, use this formula, which is you count it, okay, you calculate it as you want to calculate the normal binary, and then you divide it by the 2 power of number of fraction number, which is 15. So just have to calculate 2 to the power of
Okay.
what bit? What bit is this? This one.
What?
What bit is this? 2 to the power of?
2 to the power of -1.
This one. This one.
Where I cannot see it, doctor?
We can see a cursor.
Here. Okay, I'm not only using cursor, I draw the arrow here. This bit. This is 2 to the power of?
No, 2 to the power of 0, doctor.
No.
2 to the power of 14.
2 to the power of 14. You have to check back. Okay, you have to catch up on how to calculate this. Okay, this is 2 to the power of 14 because we have from here 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7, 2 to the power of 8, 2 to the power of 9, 2 to the power of 10, 2 to the power of 11, 2 to the power of 12, 2 to the power of 13, and 2 to the power of 14. Okay, all these bits are 1. So we have to count, we have to calculate, add up everything here like this. 2 to the power of 14, 2 to the power of 13, 2 to the power of 12, okay, and so on until you get 2 to the power of 0. Okay, calculate that and divide by 2 to the power of 15. And then you got the answer. Okay? Okay?
Okay, just got you, doctor. I'm just like a little bit confused right now, but yeah, I understand this.
Okay, this is serious. This is serious. Okay, I didn't expect that you cannot understand this, and I'm a bit worried if there are still people who are not understand this. Okay. But not answering my question when I say, okay, no problem, you have questions, right? So this is basic. Okay? This is basic that you're supposed to have understand before you come to this class. And we're not supposed to repeat this in the class. So please catch up. Okay, please catch up with the rest of the class. Okay. I know you might have forgot it because digital electronics is quite long time ago, but you're going to use this a lot, not only in this class, but also in the lab, in the microprocessor lab, in the microprocessor class, and in the other class, like in the embedded processor class, embedded system class. So as much as you are struggling, okay, I am struggling too. Like I wanted to help you. I wanted to do the video for you, but I don't want to be the only one who is helping here. You have to help yourself too. Okay, you have to catch up. Don't wait until I pick your name and found out. Okay, please catch up. Not only for a moment. I'm not saying this only for a moment. For every one of you. Okay. I know there will be more people who are not understand this. All right. We are now 9:17, but still here. Okay. Don't get demotivated. Okay. Don't get demotivated.
Doctor,
Yes.
instead of using 2 to the power of 14 plus and the rest, can I use 2 to the power of 15 minus 1 over 2 to the power of 15?
Minus 1. Oh, okay. Okay. Sure.
Oh,
But
okay.
this
Thank you,
is just
Doctor.
so that you will get something like this, right?
Yes.
Yeah. But just to make it into the formula, right?
Yeah.
So it's written like this.
Yeah, but Doctor, to get the same answer, you have to start from 2 to the power 15, not 14.
You mean like this? 2 to the power 15 minus 1. 2 to the power 15.
Yeah, for this one, it will not give you the same answer if you start from 2 to the power 14.
I don't understand.
Yeah, like this one starts from 2 to the power 15,
To the power
right?
of 14.
Yeah, but it's not the same answer, right? Because you'll have
Not
15,
the same
14,
answer
and
with? Not the same answer with?
if you start 2 to the power 14, 13, like this.
Okay.
I mean, this one you will get, if you, the one you did on the left-hand
Yeah.
side, you will get 0.9984.
84. Okay.
And this, the other one, you will get 0.49,
99.
then 69.
0.99.
4 nines.
69. 4 9. 4
Yes.
9.
No, it's 0.999969.
0.99996.
Another 9.
Okay. 49999. 69.
So 69 of this.
That will be, of course, there will be like difference in the representation because that will be the error that we will learn later. Okay?
So
Because
this formula is just approximation.
yes, because not all quantity can be represent exactly, okay, in the binary. So there will be error. But if you want to get a smaller error, you have to be more precise with a longer fractions in the binary. Okay,
Yeah, okay.
who is speaking now?
Masla.
Okay.
Okay.
Okay. Okay. Now let's move on to the next, which is the Q7 operation. Now we're talking about the Q7 multiplication, right? So when we do multiplication of 8-bit and 8-bit, we will get a 16-bit, right? But we want to stay using the 8-bit answer. So what should we get here? What should we do here is to maintain the Q7 format. Okay? To maintain the Q7 format, we must have 0 number of integers and 7 fraction. Okay? 0 number of integers and 7 fractions. So when you multiply Q7 with Q7, you will get Q Q1 14. Q1 one integer and then 14 fractions. Okay. So if you want to maintain the Q7 format, we must truncate or only take out this part of the answer. Means you cut out the rest of the remaining bits. Okay, from bit 0 to bit 6 here. Right? So here in this example, okay, the multiplicand here is 0.5. So this is equal to 0.5 in decimal. And we want to multiply with the multiplier here, 0.75. And then the results, you will get 0.375. So this is 0.375, which is 0.011 and then 000. All right, so in hardware, remember I said your hardware wouldn't know if the number is Q format or the number is positive or the number is negative. The hardware wouldn't know that. Hardware only store 0 and 1. Okay, without the point. The point is imaginary. So in the hardware, these bits are only in hexadecimal, we call it 40. Hexadecimal, you see hexadecimals like this, right? 4 bit. This is 40. This is 60. And this is 1800. 1800. This is what the hardware see. Or if we just translate this hexadecimal to decimal, you will get this is 64. Even though this is supposed to be 0.5 in the decimal. Okay. As a designer, you want this to be 0.5 in decimal, but the hardware will see this as 64 in decimal. Okay. This is 96 in decimal, and this is 6144. Okay. So, I mean, the results in the 16-bit will be 6144. Okay. But to stay, but this is what the designer wants. So we want to stay in the 8 most useful bits. So we only keep the bit from 7 to 14. For Q7. Because when we multiply 2Q7, so the integer part will double. And then the fraction part will also double, but we truncate the fraction part and only take these 7 bits from 7 to 14. Sorry, from 7 to 13 for fraction, right? And bit 14 is the sign bit. All right. Now that is when we have the exact results of multiplication, where we can just truncate the rest of the bit here because it's 0000. Yeah, 0000. 6 bit of 00, a 7 bit. But what if our multiplication results is inexact? So multiplication of Q7 to Q7 format is inexact. So what we can do, we still taking the bit 7 to 14. We still truncate the bit 7 to 14, but we need to round. We need to round the fraction here. We need to round the fraction here because we still have values here. We still have values here, so we round it to the nearest bit by adding 1 here. Okay, everyone? And for the inexact Q7 multiplication, we always add 1 at this bit position for rounding. This is position what? 6. So we always add 2 to the power of 6 to the results for rounding. Right? So it will produce a number that is closer to the actual number. So this is the actual number. Okay, this is the actual number. And when we truncate the number from 7 to 14, we have to round the number to make it close to the actual number. Hold on. Okay, so we add 2 to the power of 6. Questions? Now? Questions? Okay, no questions. Right? We add 2 to the power of 6 to round the number to get it close to the actual number. Anybody want to ask questions? Azlan? Muhammad Azlan? Right.
Asal?
Yes.
No.
Muhammad Azlan ada questions? Ada soalan?
Aku tak boleh unmute. Betul cakap aku tak boleh unmute je.
Tak boleh mute.
You just... Oh. I am speaking. Okay. No question. I
No
cannot
questions.
mute.
Oh, cannot mute. Alright, okay, no problem. Hopefully no background sound from your side. Alright. Now let's see the next slide. So when we truncate and round a value, okay, of a long fraction bit, we will get an error. Okay, we will get an error. Okay. And the error percentage is calculated as the exact value minus approximate value, and that will be in the absolute value, and we divide it by the exact value and multiply by 100 to get the percentage. So what is the exact value? The exact value is the expected value. What you are expected value, and the approximate value is the value that you get. Okay. The results, the value that you got, and divide that by your expected value, and then times 100. So truncating takes 8 top bits. Okay, so just like this. When we do the truncating, so the error can be calculated like this. So what is this? 0.11, 0.11. I think what is this value? Oh, okay. So this is 0.1000100 in binary. In decimal, sorry. In decimal, this is 0.5 0.53125. And here, value B in decimal is 00. 0.21875. Okay, so when you calculate these two value in decimal, you are expecting the results. Okay, the result will be 0.11621. Boleh ambilkan ni, dia bising lah letak dekat luar. Okay, you are expecting 0.1162109 and so on. So you are expecting this by calculating the decimal of A multiplying decimal of B. But in the results that you get, okay, when you truncate, so you get 0.0001110. This is in decimal is 0.109375. Right? So we can calculate the truncating error here by calculating the value that you calculate from decimal multiply decimal minus the value that you get when you truncating, and then divide by the value that you are expecting, which is the value that you calculate from decimal multiply decimal, and then times 100 for percentage, and you will get the error is 5.9. That is very big. Okay, but when you add 2 to the power of 6 here, when you try to round the number, okay, the error percentage has fall to 0.8, okay, 0.8%. So you can say that the rounding process, okay, reduced the error. Okay, it reduced the error quite a lot here, 5.9 to 0.8, but it needs extra step. It needs extra step. Like the one that we discussed just now, this one. So if we calculate it like this, okay, the error, the value will be like this. If we calculate it like this, the value will be 0.9999. So the value will not be the exact value. Okay, it will be like there will be like what do you call that? Okay, tolerable error. Tolerable error. Okay, between the value, because you are working with a binary here. Okay, hope that's clear about the error. Any questions about the error? Any questions about the error? Okay, hope it's clear.
Is there
Is there
any unacceptable amount of error in the system?
Acceptable amounts of error in the system is depends on you. It depends on the designer. Because you design the system, so you design the margin of error. Okay?
It's not like a standard.
No, there's no standard to it. If it's just a system that could accept big error, doesn't need precision. Okay, like if the system is taking, if the system is taking temperature, for example, okay, if the body temperature 37 and 36 is the same thing. If you as a designer would think 37 degree and 36 degrees the same thing, so your margin of error could be big, right? Because that will be like 1.0 different, but it's okay, you don't mind. But if you really need to be precise, you think 3.6, that 36.5 and 37 is a big difference, then you have to you have
the
to
error.
minimize the error. So it depends on the designer. Hope it
Thank you,
helps.
Doctor.
All right. So now we have less than 30 minutes to go. So we have practice here. We have the practice here. So write square root of 2 in Q15. So first you have to find out what is square root of 2. It is, right? So change this to the Q15. And then same goes to the pi here. So pi is 3.142. Then change it to the Q412. And then find the largest positive number in Q15 format. This is done with moment now, right? It is 0.99 and so on. But don't write this like this in the test or final. 0.99. Don't write dot dot dot. Okay. Maybe the question will ask you, okay, how many, like maybe 4 decimal number. So you have to find the number up to 4 decimal number. And as what we will calculate just now, we will accept both 0.99. If we calculate it as 2 to the power of 15 minus 1 to the power of 15 divided by 2 to the power of 15, or we calculate it as 214, 213, and so on. Okay? Probably it will only ask for 2 decimal number because it will be the same. All right. So that is for the practice. I'm just going to skip this. If you have question, you can ask later. Okay, Muhammad outside is asking, shouldn't the first one be Q115? Okay. We are following this one, right? Remember? We are following this one. So for 16-bit number, 1 bit is reserved for sign. So means we don't have any integer, no integer, and only fraction. And since we already use 1 bit for sign, we left with 15-bit for fraction. So that's why it is called Q15 or Q015. Okay? Not Q115. Because we reserve 1 bit for sign. Okay. Okay. All right. Good. Okay, now we're going to move to the floating point. Okay, floating point, everyone. So fixed point means you already fix the point to be between how many bits of integer and how many bits of fraction in a system. So that is the fixed point. Floating point means it can be any number, and the point can be moved, can be float. Okay, can be float to left or right. So that is floating point. Okay, means the binary point floats, okay, to the predefined position. And this process is called the normalization. So this process is called the normalization. All right. So sorry. Yeah. So we can float the binary point here, but we need to add how many bits we have moved. Okay. So here 5.25 is written like this. 101 is 5.01. 01 is 0.25. Okay, 0.25. So this is 1 over 4, right? So 0.25. Okay, so this is 5.25. This is equal to 10.101. Okay, means we shift, okay, the binary point 1 bit to the left. Okay, when we shift the point 1 bit to the left, means we can write it as 10.101, okay, multiply, okay, times 2 to the power of 1. So this is how many bit we move. How many bit we move. Okay, to the left is positive. To the left is positive. To the right is negative. Okay, this one. Okay, we move another one bit 1.0101. This is equal to 5.25 if we write it like this. 2 to the power of 2, and this also equal to 0.10101 times 2 to the power of 3, because we move it 3 times from the original one here. 1, 2, 3. 2 times. Okay. All right, so this process is called the normalization. Okay. So this is how your binary point floats. It floats. All right. 101 0.1. So the binary point floats from here to here, and we will say this is times 2 to the power of minus 1. Minus 1. Okay? Right? Okay. Okay, learning about the floating points part. Floating point part, sorry. Floating point parts. Okay, it's very hard to say that. Floating point parts. Okay. Here is example when we use decimal. Okay. Decimal floating point. Okay. In decimal floating point, we have the sign, we have the significance. So this is significant, but now it's called as back then it's called as mantissa, and we are still calling this the mantissa. Okay, the mantissa. Some people call it as the significance, and after the times here, that is the radix, and here is the exponent, and we also have the sign of exponent. Okay, so we can write it as, okay, the original number is x. Okay, could be positive, could be negative, and this is equal to the mantissa times, okay, the base, okay, which is the radix, and the exponent. Right, so this is how we write the floating point in decimal, and it could also be in binary. So in for computer, because floating point needs a standard format. Okay, in many system we are using a double precision format, which is 64 bits floating point. But in this class, so 64 bits is too long, so we are going to use single precision formats of the floating point that is followed the IEEE formats, IEEE standards, sorry. So we are going to learn about single precision format, which is 32 bits, okay? For fixed point, we might focus on the 16-bit, which is the Q15, okay, or any variation of the 16-bit Q format. But for the floating point, we're going to use the 32-bit single precision format. So in the 32 bits, the leftmost bits is of course reserved for the sign. Okay, it could be 0, it could be 1. And then we have the exponent, okay, which is bias 127. Okay, so the original one must be added to 127, right? The exponent value. Okay. And then the rest is the mantissa fields, or the significant, the normalized binary number. Okay. Means we have okay, for binary number, we only put the fractions here. Okay. We only put the fractions. Okay, let's take the example. I'm not sure. Okay. Let's take the example of the simple one that we used just now, which is 0, 0, 1, 0, 1, 0, 1, 0, 1. 1, 0, 1, 0, 1. So if you want to use the IEEE single precision format, we have to move this bit up to here. This mantissa part only, now we have 1.0101 times 2 to the power of 2. Okay, this mantissa part only keep this value 0101. Okay, 0101. And then the exponent, 8-bit exponent here, okay, you have to add to here, and then you have to add 2 with 127. Okay, because we bias 127. So this will be 129. So change it to 8-bit and put it here, right? So 10000000 is 128, right? 8 to the power of 2 to the power of 8, right? So 129 is 10000001, right? Here, 8-bit. We have to bias by 127. So this value adds 127. And then this part is the mantissa part is written here. Okay. So that is how, so here this is a positive, so sign bit is 0. So when we translate the single precision format to the decimal, okay, remember to minus this 8-bit with 127, and this is only the fraction, okay? The integer part is always 1. Okay? Integer part is always 1. Right? For example here, okay, 1 at the sign bit means this is negative number. Then 10000001, this is 129. So for the exponentiation part, this is 2 to the power of 129 minus 127, because we have bias here, bias 127. So you got the exponentiation part is 2 to the power of 2. And then this is the fraction part. So the fraction part is 0.11. Okay, this is where this is only the fraction parts, means the binary point is here. And the integer part is always 1. So you calculate this. This is -1 times 1.11 in binary. Change it to decimal. That is 1.75. And this is 2 to the power of 2, which is 4. So we calculate this and you will get -7. So we can represent -7 in the IEEE single precision format to be like this. This 32 bits represent -7. Okay. So there are also special value in the IEEE bit patterns, which is the value of positive 0, -0, 1, 2, positive infinity, negative infinity, and so on. Okay, this is for you to read. And there's also the variation of the IEEE format, which is half precision. Okay, half precision is 2 bytes. Okay, 1 byte is 8 bit. So 2 byte is 16 bit. So that is half of 32. Half of 32. That's why we call it half precision. And then we also have the B float. That is difference in the significant bits number. And then single precision. Okay, that is 32 bits, where the significant bits is 23, and then 8-bit exponent, sign bit 1. And then double precision, that is 8 bytes, means 64 bits. And then we have double extended, okay, and also quad, means 16 bytes. Okay, 16 bytes. So double precision, which is the 64 bits, is more common. But in this class, we are only discussing the 32-bit, the single precision, because it's too long to do in exam and test if it's 64 bits. Okay, you can check this. You can check this, the single versus double precision. You can go to this website where you can do programming online at the online platform and check the output here. Okay, if we are using a double precision, mean we are using the double variable, okay, our results will be more precise, means longer fractions. Okay, if we only use the single precision, where we just write the float here, floating number, and it is less precise. Okay, this is how we are forced to use the single precision. You don't have to worry about the programming here. Is just an activities in class. We're not asking programming in the class. Okay, we're not asking the code, how to write the code in the test and final. Okay, this is just an activity in class so that you can check, okay, the precision value. And you can also check the single precision bit, okay, of 1/3 here. Okay, floating point of 1/3. You can have this value, okay, and this is the 3E that you see here is the value that is stored in the hardware. This is in hexadecimal. Okay, sorry, I'm a bit rushing now. We're losing times. And this is doing the same thing as this one, but in double precision. Okay, and then we have some practice. So we can try to write the number of 17, 0. Okay, this is 17 in decimal. Okay, so it's just 17 in decimal. Okay, in single precision floating point. And then we can try we can also try to write pi in the half precision floating point. All right, I'm not going to force you to submit any of these activities. Okay, if you try it and you couldn't get it, or you want to check what is the correct answer, you can ask me in the next class, right? And you have to know the difference between the fixed point and the floating point. The fixed point is suitable for the simple circuit, while the floating point is suitable for the complex circuit. Again, you might ask me what is simple circuit, what is complex circuit. That is depends on you as a designer. But if you want to, if you have a powerful device to implement your circuit, like if you are using FPGA, like a complex circuit could be defined as a simple circuit. If you are using an Arduino, a simple circuit could be defined as a complex circuit. You got what I mean? Okay, it depends on what resources you have. Okay, either it's FPGA, either it's CPLD, either it is a microprocessor like Arduino. Okay, it depends on what you have. Then you could define what is a simple circuit or a complex circuit. Okay. So the fixed point arithmetic will only need a small silicon area and consume less power, while the floating point needs a large area. Of course, if we are following the IEEE standard, we need 32 bits at least for the single precision. So of course, they will need larger area, and larger area means you need more larger area. Longer bits mean you need more wire on your circuit, because one wire will carry 1 bit. Okay, so there will be more power consumed. And the fixed point is less accurate compared to the floating point, because we have more of the fraction bits on the floating point. Okay, and then the fixed point is smaller range of value can handle small range of value, while the floating point can handle bigger or wider range of value. Okay, like you can make a comparison between fixed point, the same fixed Q15 with half precision of floating point of IEEE, because this is also 16-bit. So both is 16-bit. Q15 is also 16-bit. Okay, but the range that it can handle could be different. This is from -1 to 0.99, and this is, okay, find it yourself. And then the rounding can improve the accuracy of fixed point number at the cost of additional hardware. That is the drawback or the disadvantage of the fixed point. It has the accuracy problem. It can be fixed using the rounding, but rounding will add another circuit, another additional hardware in your circuit. Okay, because it needs another calculations. All right, so that's all for fixed point and floating point. Remind me in next class on Thursday to discuss about these activities that we couldn't go through together before we start with class on Thursday. So it's now 10 a.m. I'm sure you are ready for the next class. So that's all for today. If you have any questions, yes.
Moment, I just want to apologize for the previous.
Moment,
when
you don't have
called my
to.
name, yeah, just when you called my name, I was just like woke up and I didn't know what is going on, literally. So I'm so
okay.
sorry.
It's okay. It's okay. In this class, you don't have to be sorry, but it is nice to receive and apologize from you. Okay. I need to hurry up because some of you might have class after this. So
Okay.
yeah, we talk again. We talk soon in the WhatsApp. Okay. So
Okay.
don't worry about it, Moment. I'm not mad at you. I'm just a little worried.
No, it's okay.
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 Okay,
Thank
that's
you.
all, everyone. Attendance will be taken from the report of the WeBEX. Don't worry about